Okay, so the plan for today is to finish section 11.9, get a start on 11.10. I know it's a math textbook, so it's kind of strange that we call 11.10 instead of something else, but 11.10 Taylor MacLaurin series, and then possibly look at some applications of Taylor MacLaurin series. So I apologize that I had to cancel class last week, but I posted two chapter 12 supplement videos to the YouTube playlist. Um, so I know that's the material after all of this, but it's kind of unrelated material. Chapter 12 really starts a new set of ideas. So I've mentioned in the past that it was kind of historically a Calc 3 set of material that got pushed into Calc 2 once we added a little more material into Calc 3. Um, so check out the YouTube playlist for those supplemental videos. They'll likely be the last supplemental videos unless there's something on series that we need to wrap up. On Wednesday, we'll kind of finish or review chapter 11 on series. If we have any last ends from today to tie up, we'll do that on Wednesday as well. And then Monday the 5th will be just kind of a course wrap up. If there's any last topics we need to cover or last examples, anything like that, or if there are any questions about the final exam, anything like that. So the final will be available from this coming Friday in 4 days. I know it's a very quick turnaround. We were on spring break. It feels like not too long ago, and then we're already in finals week almost. So this Friday through the following Friday, the 9th. Um, Finals week proper goes from Tuesday the 6th through the following Monday. Um, so I'm giving you, you do have Tuesday through Friday of the proper finals week that you're certainly free to take the exam during that time. But I'm opening up a little bit early so that you do have that full weekend, the second, third, and fourth, if weekends work better for you. Um, that being said, I would strongly recommend to plan to take it no later than Wednesday of finals week, the 7th. That way, if anything does go wrong, you still have plenty of buffer, plenty of time to get things worked out, reach out to me, and so on if anything does happen. It's going to be the same setup as the midterm exam taken on WebAssign. Sample exam will be posted this week, and you may use a formula sheet. So that could be a formula sheet that you create yourself. You could use the series kind of workflow sheet if you wanted to. So whatever works for you, you can write your own. You can, use one of these other formula sheets or uh, documents from the course if you would prefer to do that. So that's our last couple of class meetings. The quotes of the day today are uh, meant to highlight two aspects of the way that people think about a bit about the philosophy of mathematics. So there's this idea of mathematical formalism, where the thought process is basically that mathematics is human created. It's essentially a set of rules that we implemented, and it's the logical system we implemented, um, and that we created it, and it's not something inherent to the universe. Versus mathematical Platonism, named after Plato, um, the Greek philosopher, where the thought process is something more along the lines of these mathematical ideas are somehow inherent in the universe and we're discovering them. I think of it as a little bit like chess versus gravity, right? I think very few people would say that the rules of chess are somehow inherent to the universe and we discovered them. I think anybody who would argue that would have to wrestle with the fact, well, then can we really say that we discover anything? And uh, but but kind of like we create the rules of chess, and just because we don't see all of the consequences of those rules immediately doesn't mean that um, the rules of chess are inherent to the universe and we're discovering the rules. We create the rules and we can discover consequences of those rules. We can discover that this opening is good and this opening is bad, and this end game should be played this way to play it optimally, so on. Versus something like gravity. Gravity is going to work the way that gravity works, whether you like it or not, whether you know about it or not. We can look at chess and say, oh, well, this rule makes the game too one-sided, so we'll change it and we'll we'll make an adjustment to the rules here or there if we wanted to. You can't do that with gravity. Gravity is going to be the way that it is. So the two quotes to highlight this, one by Leopold Kronecker, God created the integers, everything else is the work of man. In other words, saying maybe there's some structure that like integers, one thing, two things, three things, etc., or somehow fundamental. I would even argue that that's not so clear. If you say one apple plus one apple is two apples, well, why do we call this an apple? It's because it's a nice self-contained thing that we can put on the counter and doesn't rot. If you cut it in half, it starts rotting, so we don't call that an apple anymore. So um, I think that can even be debated. Versus Eugene Wigner, whose name I'm probably butchering, but um, he has a paper entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." So I kind of turned that into a quote, adding there is evident an unreasonable effectiveness of mathematics in the natural sciences. And the argument, at least one part of his argument, proceeds something along the lines of like, we discover something else in the natural world that we find interesting, we develop a mathematical model for that thing. And of course, the mathematical model we develop, matches that thing fairly well. It describes the thing fairly well because we made it to do that. But then we find some other natural phenomenon that's kind of related to the first thing in a tangential way. And we actually find that the mathematical structure we created for the first thing kind of tells us something about the second thing that we wouldn't expect. And something like his argument is, well, if we were just tailoring the mathematical models to the first thing that we see, then when we see something else come up, we'd expect to have to go back to square one, rewrite our mathematical model to incorporate these two things now that we want to incorporate. And mathematical models seem to like describe new phenomena better than we might expect them to if we were just using those whatever human-made constructions to do one very particular specific thing. I tend to land more on the side of mathematical formalism, that we basically create mathematics, and the reason it does such a good job of modeling the natural world is because if you have 10 mathematical ideas and one of them helps you build bridges and make antibiotics and medicine, and the other nine are like some very abstract things in number theory, well, you're going to get paid a lot better if you pursue the one where you can build bridges or cars or watches or things that people want. And not too many people are going to want to pay you to sit around and just think about number theory or topology or something like that. So of course we have more people going into those areas, and the research is heavily geared towards mathematics that can be directly applied to the real world. So that's kind of my feeling, but there are a lot of people much, much smarter than me who fall on the other side as well. So I don't think this is in any way a settled discussion. But anyway, just an interesting little thought. Okay, so let's continue on with 11.9, representing functions as power series. And we're going to look at this example. We want to solve a differential equation, really an initial value problem, but in our differential equations section, we talked about equations like this, y prime equals y, with the initial value y of 0 equals 1. But here we're actually going to solve it using series. So as a little aside, we should know what the solution to this is, right? Y equals e to the x. Y prime equals y. The derivative of e to the x is e to the x. And y of 0 equals 1. That meshes, right? We would get something like y equals a times e to the x to solve the differential equation and pose the initial condition, and we get y equals e to the x. So we know that the solution is y equals e to the x, and something that I mentioned is that these solutions, under some reasonable conditions, are also unique. So if I find another solution, maybe in a different form, to this initial value problem, that's just got to be another way of writing e to the x. Okay, so let's try to use series to solve this. Okay, so let's suppose that y equals sum n equals 0 to infinity, a sub n times x to the n. Then what's y prime? Well, on the interval of convergence, we can differentiate under the summation sign. We get some, well, not really n equals 0 to infinity, because the initial sum was a naught plus a1x and so on. But let's fix this bottom index here, n equals 1 to infinity, a sub n times n x to the n minus 1. Or this is like a1, or well, 1 times a1 x to the 0 plus 2 a2 x to the 1, and so on. Or this would be like some n equals 0 to infinity of some stuff times x to the n. So this would be like the n equals 0 term, the n equals 1 term, just re-indexing so that my n from the index is associated with the power of x again. But then my n equals 0 term would have to yield a 1a1 as the coefficient, or that's n plus 1a subscript n plus 1. Let me write this a little bigger because I'm squeezing this stuff in here a bit. N plus 1, a subscript n plus 1, x to the n. So then when n equals 0, I get 1a1 x to the 0. When n equals 1, I get 2a2 x squared, or x to the first, and so on. So we see that this is what y prime is. So y prime equals y, what does that tell me? Well, that tells me that some n equals 0 to infinity of an x to the n equals some n equals 0 to infinity of n plus 1 an plus 1 x to the n. Well, this equating of two sums, I basically have on both sides like a constant term and then a linear term and then a quadratic term and so on. I can equate the coefficients of those as well. If I really wanted to drive the point home, I could write both of the sums as a difference of two sums on one side, and they will both converge on the same interval of convergence as the original one. And then I could wrap them under the same sum, and I would get sum of a bunch of stuff equals 0. So that would be the more formal argument, but we see that an, it looks like n plus 1, an plus 1. And this is for n equals 0, 1, 2, etc. Or I see that an plus 1 equals 1 over n plus 1 an for n equals 0, 1, 2, etc. So I end up with this thing here. So like if I know what, say, A2 is, then I can find A3 in terms of A2 and then find A4 in terms of A3. I can bootstrap my way up from that point forward. This is often called a recurrence relation. So if I can find a certain A sub whatever to kind of anchor myself, then I can find all the future ones off of this. I suppose I could also find all of the past ones off of this as well. So what is A naught then? Well, on one hand, I know that y is some n equals 0 to infinity, an x to the n. What I haven't used yet is y of 0 equals 1. So what is y of 0? Well, So y is a naught plus a1x plus a2x squared and so on. Everything except the a naught has a power of x in it. When I plug in x equals 0, I'm left with just my constant term a naught. When I plug in the center of the series, all of the other x terms go away. I just get my constant term left over. So on one hand, from the series, y of 0 is a naught. And on the other hand, from the initial condition, y of 0 equals 1, y of 0 has to be 1. So I get that a naught is equal to 1. But now I can use my recurrence relation. When say n equals 0, I have a sub 0 plus 1 in the subscript gives me a1 equals 1 over 0 plus 1 is 1. A naught, which is just 1 times 1, or 1. So a1 equals 1. When n equals 1, I get a sub 2, 1 plus 1 is 2, equals 1 half a1, or that's 1 over 2. When n equals 2, we'll do a couple more of these. So we see the pattern. I have a3 is 1/3 a2, but a2 is 1 half, so that's 1/3 times 1 half, or 1 over 3 times 2. When n is 3, we have a4 is 1 over 4 a3, but a3 is 1 over 3 times 2. That's 1 over 4 times 3 times 2. And I think we see the pattern that a sub n is 1 over n factorial. That works for these ones. That also works for this one, that a naught is 1 over 0 factorial, because 0 factorial we take to be 1. Or I can actually come all the way back up here and say that the series solution to this differential equation is y equals sum n equals 0 to infinity of x to the n over n factorial, right? An is just 1 over n factorial. And hey, look at that. Through a differential equation, solving it two different ways, a kind of a direct attack with series, just grinding out what the series solution has to be, versus previous knowledge, we now have a power series representation of e to the x. My radius of convergence for this series is infinity. That might be a good thing to just check for practice, but we'll be this will converge on the whole real line. Right, we have a kind of a power function, or I suppose an exponential function in the numerator, but we have a super exponential in the denominator with this n factorial. N factorial works kind of like n to the n. So my terms do get small enough fast enough as I go out into the end of a series. Okay, so with our newfound power series representation for e to the x, let's try to answer this question. Let's try to compute. Well, that didn't get a whole lot. I thought I was going to make it a bit more visible, but didn't help a whole lot. Let's compute this integral. So integral of e to the x squared dx. This is one that that I think I've mentioned before, that you've probably seen before, is an example of an integrand that is, in theory, perfectly well integrable. It's a nice continuous function, no problems. But we can't write down in a nice closed form function what the antiderivative is. But we can write down the antiderivative as a power series. So e to the stuff becomes sum n equals 0 to infinity of stuff to the n over n factorial. And this is x squared. So we're integrating this dx. We can we can interchange our summation symbol and the integral symbol, provided we're on the interval of convergence. But again, since the power series for e to the x converges on the whole row line, no issues here. Now the integral comes inside the 1 over n factorial. Remember, the integral's variable is x. So the integral doesn't care about the 1 over n factorial. That's just a constant as far as the integral is concerned. So that comes out. And then we're looking to integrate this thing up here, x to the 2n. Importantly, remember this is dx. So it's not dn, where this would be like integrating an exponential type function. This is dx, so we're integrating something like a power function. Really easy to get confused with which one is being treated as the variable versus the constant in which of the cases. Right now, our focus is on the integral on the inside, so we're thinking of x as the variable, n is a constant. So this is just like x, x to the 4th or x to the 10th or something like that is what we're thinking of inside the integral. So I integrate this, I get x to the 2n plus 1 over 2n plus 1 plus constant. And that's what we have. So it's certainly not the nicest looking function ever, right? It's not in what we call a closed format. It's you can't write it as like a finite number of things like power functions, exponentials, trig functions, that kind of thing. A finite combination or composition of those. It's written as an infinite series. So, for a function like this or an integral like this, that type of function is about the best we can do. There might be other functions where maybe we would go through this and we would maybe recognize the series that comes out the other side, and we might say, oh, okay, I can rewrite that as in a nicer, cleaner format, but not really the case here. And as an aside, we're not saying that this cannot be written in closed form because I don't happen to recognize this series at the end here. It's provably the case that this cannot be written in closed form, but I'm just making a note that, if we had integrated e to the x the same way, we would most likely come out with something at the end that we recognize readily as something like e to the x again. But that didn't happen here. Okay, so let's jump to our kind of last major topic, really in the course, I suppose, really the last major Calc 2 topic. And that's the topic of Taylor series and MacLaurin series. So we'll spend the rest of today and probably actually most of Wednesday's class on these topics. So what if I want a power series representation centered at A for a function? We saw that in our 11.9, we were able to represent some functions as power series. But we had kind of like every one of them was an ad hoc method, right? Maybe one function, I realized that I can make it look like a geometric series. Or another function, like I realized that I can plug it into a differential equation and like make that work. But do I have like a more formulaic or algorithmic approach where I can say, just take whatever function it is, put it in this mechanism, turn the crank, and get your power series out the other side? I don't want to try to, every function that I come up with, try to find some creative way to turn it into a power series. I want something that will work for, say, roughly speaking, any function you're given, you do it the same way, and it cranks out the power series representation. And that's what we're trying to do here with Taylor-Maclaurin series. So my goal is to find a power series representation for a function f of x. So we want something along the lines of f of x equals sum n equals 0 to infinity, cn x minus a to the n. Okay, so what can I do here to make the right-hand side simpler? What would make the right-hand side? Well, one thing I could do is I know that if I plug in the center of the series essentially all collapses down to just one term, right? This is like c naught plus c1 x minus a, and so on. Right. If I plug in x equals a, then all of my terms from the second term on, from the linear term on, go away, and I just have c naught. Well, that's kind of nice. I mean, I figured out that if this power series representation is going to work, let's suppose that we have a function that's nice enough that all of what we want to do with it is available to us. I figured out what C naught has to be. If I plug in A on the left, I plug in A on the right, I get f of A equals C naught. That means that the first coefficient of my power series, C naught, it has to be f of A. That's what it's got to be. Well, that's pretty nice. But I mean, I've only got one coefficient though. I still need to figure out C1, C2, C3, and so on to the end of the line here, right? I need to figure out infinitely many of these. Well, one thing that I might notice is if I differentiate, then my second term here effectively becomes a constant. Well, it does become a constant if I differentiate. My first term differentiates off, and everything from this point forward still has at least one power of x minus a. So these still have at least one x minus a. This is constant, and this goes to 0 when I differentiate with respect to x. So I get what almost looks, philosophically or kind of loosely speaking, what almost looks like the same structure, constant plus a bunch of stuff with x minus a, except that everything is kind of shifted down, right? I kind of got rid of the first one in the line, shifted everything down one. So what is f prime of x then? So taking d by dx on the left-hand side, that's f prime of x. On the right-hand side, that's, well, kind of sum at n equals 0 to infinity of cn times n x minus a to the n minus 1. But again, we can maybe start this at n equals 1. Oh, and what does this look like? Well, if I differentiate this power series up here, the c naught differentiates to 0. My c1 times x minus a, so I have a c1x term and then a minus c1a term. The minus c1a differentiates to 0, and my c1x just differentiates to c1. And then I have 2c2 x minus a plus 3c3 x minus a squared, and so on. So if I do f prime of a, what does that give me? Well, if I plug in a, all of these are 0 at a. My initially first term, that constant c naught, differentiated to 0, and all that is left is c1. Now let's not jump to conclusions too quickly here. It can be easy to do that. Let's do a couple more of these. We might just think that like C2 is f double prime of a, C3 is f triple prime of a, C4 is f fourth of a, the fourth derivative. Doesn't close to that. It doesn't quite work out that way though. So let's take a couple more derivatives. What's f double prime of x? I'll stop working with the series representation and just work with this representation now. My C1 differentiates to 0. My C2 term, 2C2x minus a, differentiates to 2C2. My 3C3 term differentiates to 3 times the 2 comes down, times 2, C3 x minus a to the first, and so on. Everything after the C3 term also has at least 2 powers of x minus a. So what's f double prime of a? This is 0. That constant differentiated to 0. At a, all of these are 0. The C3 term and on all have at least 1 power of x minus a. So they all go to 0. All that's left is 2C2. And I see I have a little bit of rearranging to do here, that C2 is 1/2 f double prime of a. So not quite just f double prime of a, but 1/2 f double prime of a. But what's C3 be? If I take the third derivative, 2C2 now differentiates to 0. The C3 term, 3 times 2 times C3, x minus a differentiates to 1. And then I'll have some constant C4 times x minus a to the first, and so on. All of this stuff will have at least 1 power of x minus a in it. This is 0. If I plug in x equals a, I get f triple prime of a equals, this is the only bit that survives, 3 times 2 C3. Or it tells me C3 is 1 over 3 times 2 f triple prime of a. I might note, if I'm a little more careful with my constants in front of C4 here, C4 would have originally been attached to x minus a to the fourth. We differentiated once and the 4 came down, left a 3 in the power. Differentiated again, the 3 came down, left a 2 in the power, and then the 2 came down, left a 1 in the power here. So what are we going to get next? 4 times 3 times 2 C4 equals the fourth derivative at a. Or C4. C4 is 1 over 4 times 3 times 2, f fourth derivative at a. And at this point, I might see the pattern that, let's say, I guess what is called it, Cn is 1 over n factorial, the nth derivative of f at a. Right, and once I figure out a formula for all of my Cn's, I've determined my power series, right? That's all the information I need to know what my power series is. These are all of the Cn's. And this is for n, an integer bigger than or equal to 0. Here, of course, the 0th derivative of the function is just the function itself, and 0 factorial is 1. Now, personally, I think this is kind of surprising, because we think of f of x, there are infinitely many points, infinitely many inputs and outputs, and not just infinitely many, but uncountably infinitely many. So if I say, like, for f of x equals sine x or e to the x or something like that, if I say, okay, I can plug in 0 and get an output, what's the next number that I can plug in after 0? roughly speaking, there is no next number, right? Any number that you say might be the next number, you can plug in 0.1, well, just divide that number in half. That's still a valid real number. That could be plugged in as well. So there's uncountably infinitely many points kind of wrapped up in f of x, but we only need to know countably infinitely much information on the right-hand side to represent that function. That's kind of interesting for, kind of roughly speaking, any function that, has nice enough properties that you can differentiate it a bunch of times like this, right? All that I need to know are these CNs, and there I can say, what's the next one? C naught is f of a. What's the next possible C coefficient? Well, C1, f prime of a. What's the next possible one? It's C2, 1/2 f double prime of a. So it almost feels like cheating that we get like uncountably infinitely much information for what seems like countably infinitely much work. I think that's kind of just, you know, just very interesting and, shows you how strange infinities are. Okay, so what's our definition of Taylor series? The Taylor series for f of x, this is of course provided it converges and so on. The Taylor series for f of x centered at x equals a is f of x equals sum n equals 0 to infinity, the nth derivative of f at a over n factorial, that's what we just came up with up here, what all those coefficients are, times x minus a to the n. And this is provided that absolute x minus a is less than r, the radius of convergence. The MacLaurin series is really just the Taylor series centered at 0. So that's what the MacLaurin series is. You just plug in a equals 0 up here, and we get f of x equals sum n equals 0 to infinity of the nth derivative of f at 0 over n factorial times x to the n, x minus 0 to the n, where absolute x less than r. So MacLaurin series, just Taylor series, but the special case where the center is 0. Okay, so let's look at f of x equals e to the x. Let's find the MacLaurin series representation, the representation centered at 0. I know I need the function value, the first, the second, third derivative, etc. at 0. So what is f of 0? That's e to the 0 or 1. But that's also because f prime of x is just f of x, because that's a property of e to the x. That's also f prime of 0, f double prime of 0, and so on, right? Because e to the x is its own derivative. So all of these nth derivative of f at 0 just turn out to be the number 1. And we have e to the x equals sum n equals 0 to infinity of 1 over n factorial x to the n. And hey, that was exactly the series that we found, the series representation for e to the x that we found using the differential equation method. But here we had just a formulaic approach, right? This was much shorter, much more concise. We didn't have to know about another field of mathematics, something about differential equations, or pull in other topics from other areas. We just had a machine, we put in e to the x, we turn the crank, we find its derivatives, we evaluate those derivatives at the center, and that gives us the power series. What about the power series, the representation, Taylor series representation centered at, say, a equals 1? Well, here I'm looking for f of x, the same function, e to the x, but being represented by a slightly different series. N equals 0 to infinity of Cn x minus a or x minus 1 to the n. I have a different center. I have a similar setup though, right? I just take the nth derivative at a over n factorial for my coefficients. So I want e to the x to be f of x. F of x is still e to the x. So its derivative, second derivative, etc., are all still e to the x. But now I'm looking to say that e to the x is sum n equals 0 to infinity of what? Of the nth derivative at a, or the nth derivative at 1, over n factorial x minus 1 to the n. Or I see that e to the x is, well, f of 1 is e to the 1, or just e. And that's also, of course, f prime of 1, f double prime of 1, etc. So sum n equals 0 to infinity of just the number e, or e to the first power, just that number, over n factorial, x minus 1 to the n. And this will also converge on the whole real line. Okay, for this one, I think I'm going to write out the answer because it takes quite a while to work through all the details. If you want to work through the details for as practice with doing derivatives and so on, that's not a bad idea. But I'm going to kind of give a sketch of this one because we're running a bit short on time and it takes a while to do. So I have f of x is 1 over 1 plus x squared. And I'm looking to find the MacLaurin series. So I'm looking to write this or represent this as sum n equals 0 to infinity, the nth derivative at 0 over n factorial x to the n. And what we find is that f of 0 is 1, or 0 factorial. We find that f prime of 0, I'm looking just off of my notes here, is 0. F double prime of 0 is -2, or we could think of that as -2 factorial. Not -2 all factorial, but negative of 2 factorial, to be clear. -2 factorial, like that. Third derivative is 0. Turns out that way. The fourth derivative at 0 is, after quite a bit of hassle, it is positive, I think it should be 3 factorial or 4 factorial, right? Yeah, 4 factorial, positive 4 factorial, and so on. So what we end up with is 1 over 1 plus x squared is, well, f of 0, that's the 0th derivative. That is our constant, 0 factorial. Our linear term has a coefficient of 0, it goes away. Our quadratic term, we have minus 2 factorial is f double prime of 0 over 2 factorial. I suppose we could write this as over 0 factorial if we really wanted to be pedantic. X squared. Our x cubed term, the third derivative is 0. Third derivative at 0 is 0. Our fourth power term, we have a plus 4 factorial. That's our derivative over 4 factorial. That comes from this n factorial here, x to the fourth, and so on. Or what I really see is I have 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, and so on. I kind of see two things here. Number one, I see that had I used the 1/1 minus negative x squared trick, written this as a geometric series, I would have gotten exactly the same thing. Right? When n equals 0, I get stuck to the 0 power as just 1. When n is 1, I get minus x squared, and then plus x to the fourth. When n is 2, I guess I really should do minus there. So I see I would have gotten the same thing using this trick, but again, I was able to just use machinery to calculate this in this case. In this case, using the trick would have been a lot quicker than doing all these derivatives. The derivatives just get pretty messy pretty quickly. The other thing I want to point out is this is an even function, right? If I replace x with negative x, I get the same thing back. Why do we call it an even function? That seems like kind of a strange name for this type of symmetry, where I'm swapping x for negative x, or where I'm flipping about the y-axis and it looks the same. It's an even function because its MacLaurin series only has even powers. So there's this one-to-one kind of analogy or correspondence between even function symmetry, replacing x with negative x and getting the same thing, right? F of negative x equals f of x, or flipping about the y-axis and getting the same thing. There's a correspondence of this with the MacLaurin series representation only having even powers represented and no odd powers. If there were any odd powers represented, x cubed or x to the fifth or something that didn't have coefficient of 0, when I swap x for negative x, that negative will persist through, right? The like negative x all cubed will become negative of x cubed, and then the thing will change. But because these are all even powers, when they get the x put into them, the even power kind of kills the negative and nothing changes. The same goes for odd functions, right? If we looked at an odd function, one where f of negative x is negative f of x, or one that is symmetric under, say, rotation by 180 degrees about the origin, those are called odd functions because their power series representation will only have odd powers. So they won't have a constant term, because if you shift the whole thing up, then you rotate it around. Of course, then shifting up, rotating around is like shifting down, and that's going to be different. But it's also not going to have an x squared or an x to the sixth or an x to the 10th term if it's an odd function. Odd functions, in the sense of the symmetry, either algebraic or geometric symmetry, will have power series representations that only have odd powers represented and no even powers. So this is why we call them even functions or odd functions. We can also see why there's a theorem that if you have a general function, maybe it doesn't have a nice symmetry. Maybe it's not an even function and it's not an odd function. It doesn't have that symmetry. But you can always take a function, I mean, provided it's well enough defined and so on. You can take a function and you can split it into the sum of an even part plus an odd part. What are we basically saying there? Like, you take e to the x, it doesn't have a nice symmetry to it. It's not symmetric about flipping over y, and it's not symmetric about rotating 180 around the origin. It's not an even function, it's not an odd function, it doesn't have that symmetry. But I can write e to the x as something like f even of x plus f odd of x for two functions f even and f odd. Why does it feel like I should be able to do that? Well, I should be able to take my series here, provided it converges nicely and all that, and kind of take all of my even power terms and kind of pull them off to one side, and take all my odd power terms and pull them off to the other side, and make an even power series plus an odd power series, just two other functions that are an even function plus an odd function. So I can decompose, I mean, as long as it's not really messy function, I can decompose the function into the sum of an even function and an odd function. Um, and the power series gives us some insight into why that should be possible. I think that's a pretty surprising fact at first. It's like you take something with no symmetry and you can make it into the sum of two things that have very interesting symmetry, essentially, like say, roughly speaking, all the time, not just for a function here, a function there. But this gives some insight into why that really ought to be the case, linking these symmetries to which types of terms are left over, the even powers or the odd powers. Okay, so the Taylor series definition is nice enough. We gave a motivating example for it. But one issue we have is, again, when we start throwing around infinities and starting to talk about series and so on, we saw that there were so many little nuances with series that we had to be very careful that we didn't get too flippant with what we did with series, because we have these infinite number of terms going on. So when I'm saying something like, oh, just pull your even terms out front and your odd terms at the end, right? And we've got to be a little bit careful when we do that kind of stuff. So one important theorem is Taylor's theorem. And in some sense, this is kind of, the really important bit of mathematics here, in a manner of speaking, even though, even though this is maybe the mechanism that's used much more often practically, this is what lends the proper support to it, I would say, something along those lines. So let's consider a function f of x. And let's consider a partial sum of a Taylor series, t sub k of x, kind of the kth partial sum of the Taylor series. Here, tk of x is the sum of the first k terms, or the 0 through the kth term, if you want to say it that way, I guess, first k plus 1 terms of our Taylor series. So it's the kth partial sum of the Taylor series. We can, of course, always write f of x equals tk of x plus rk of x for some function rk of x. F of x is known. It's the function that we're representing as a Taylor series. Tk of x is the partial sum given here. So then what is rk of x? Well, it's just f of x minus tk of x. So we can always find an rk of x that makes this work. If the limit as k goes to infinity of rk of x is 0 on some interval of convergence, absolute x minus a less than r, then we say that t of x equals f of x on absolute x minus a less than r. We gave a heuristic argument of why it feels like this is the right thing to do. Or we maybe said something along the lines of, what do we prove formally up here? We maybe proved something like, if our function can be written as a power series like this, then this is what the coefficients need to be. But if I just take an arbitrary function and write it out, I mean, is that a valid way to write that function? If I can write the function as a power series, it's got to be that way. But who's to say that that function should be able to be written as a power series in the first place? Well, this is the check. We take a look at the remainder, rk of x, and if that goes to 0 as k goes to infinity on some interval of convergence, then we can indeed write the function as we can represent the function as a Taylor series using the above definition. Nicely enough, we actually also get Taylor's inequality out of this. We get a bound on the error in estimating the function by its Taylor series partial sum. So of course, anytime that I actually want to like implement a usage of a Taylor series or MacLaurin series, if I want to use this to compute something, I of course can't have the computer do infinitely many terms added together. So maybe I stop at n equals 10 or n equals 20. where should I stop? How good of an estimate do I have at that point? Taylor's inequality gives us an upper bound on the error. So it says if you go this far out into the partial sums of the Taylor series, then your error will be no more than this big in absolute value. So the error, or the remainder, the size of the remainder, the size of the error, basically what it looks like, remember we went out to the kth partial sum. So we went out to the kth term that looks like this. And this thing here kind of just looks like the k plus 1th term, right? Or k plus 1st term. We have like an over n plus 1 factorial times like an x minus a to the n plus 1. The x minus a to the n plus 1 is in absolute values because this is in absolute values. And our numerator isn't exactly the exact thing we left off, but this looks kind of like the first term we leave off. That's the upper bound for the error. That actually has kind of the feeling of the alternating series estimation theorem. It has a similar feel to it, where the error bound looks a bit like the first term we leave off. What is in my numerator here? It is the maximum of the derivative over the interval that I'm interested in estimating this on. So absolute x minus a less than or equal to d. So I'm interested in an interval from a minus d to a plus d. Over that interval, I figure out what's the maximum value of my n plus first derivative of f in absolute value. That's what m is. Plug that in and get my error bound. Now, of course, at x equals a at the center, I'm not going to have any error at all because my function has to match my my constant term there. So there's no estimating and leaving off some of the terms further out in the tail. But when x deviates from a maybe a little bit, x minus a to the n plus 1 might be a small number multiplied by some coefficient. But if x deviates from the center a lot, well, then my Taylor estimate is likely to be much more flawed, right? Much less accurate. So these Taylor polynomials, these partial sums, these estimates are going to be very close for x's near a. What do we mean by x near a? Well, that's dependent on the accuracy you require and how large these numbers are and so on. But as I get further and further away from a, my Taylor polynomial is at least has the chance to be a worse and worse approximation of my actual underlying function. Now, of course, if I have all infinitely many terms, then the two, provided this theorem holds, match exactly. But if I'm chopping it off at 10 terms, 20 terms, something like that, to get a better approximation, I either need to have more terms or I need to stay closer to the center of the series. Okay, so when we come back, we'll quickly review some common MacLaurin series. So we'll see some that we have seen before, as well as maybe a few that we haven't seen before. And then we'll continue on with this section. So let me stop the recording.